Hi, my name is Steve Fliegel, the Science and Operations Officer at the Aberdeen National Weather Service Office. This module will cover blowing snow within Forecast Builder. This presentation and the development of the blowing snow tools was a joint project between Chauncey Schultz, the Sioux in Bismarck, Tommy Grafenauer, the Sioux in Grand Forks, and myself. First, we need to start by defining the differences between blowing and drifting snow and discuss why these differences are important. Blowing snow is defined as snow lofted from the surface by the wind to a height of 6 feet or more, causing a reduction in visibility, while drifting snow is defined as snow raised from the surface by the wind to a height of less than 6 feet, with no or little visibility restriction. The impacts from blowing snow tend to be more significant than that of drifting snow. With the increased focus on consistency in the Forecast Builder era, it was quickly discovered that different offices, and even forecasters within the same office, had varying philosophies on what constituted blowing snow. For example, when snow is lofted into the air, at what visibility reduction should we mention the phenomena in the forecast? For example, less than 6 miles, less than 2 to 3 miles, less than a half a mile? Adding to this mess, there was not a drifting snow variable available within GFE, which means that different philosophies exist on when and how to utilize the blowing snow variable to account for drifting snow. Finally, the initial Forecast Builder configuration allowed offices to choose between two scientifically developed methods. This led to inconsistency from office to office and shift to shift, along with increasing the time required for collaboration. A compromise of the varying philosophies related to forecasting blowing and drifting snow is needed. After discussion with numerous forecasters and Sioux across the northern plains, where blowing snow is most common, some guidelines for the usage of blowing snow in the weather grids were developed. Basically, we are equating coverage terms to impacts. Drifting snow is accounted for by the use of the term patchy. Patchy is an all-encompassing term and can be used for no or low impact blowing snow events. For example, impacts to aviation but not the public. These impacts of blowing snow on the public sector typically start to increase as the visibility lowers and the coverage of the lower visibility increases. While it's difficult to account for both the value and the coverage of visibility in one coverage term, thinking about these guidelines in terms of impacts makes them easier to understand. Take note that a fourth category is added. 20% of pop blowing snow equals patchy, 40% of pop blowing snow equals areas, 70% definite, and 100% definite with a 1/4 mile tag. That quarter mile tag will be added during the weather creation step of the Forecast Builder process. Before looking at the details of the Forecast Builder blowing snow tool, we need to first understand the science behind the tool and what the primary factors are that affect blowing snow. As you can see on the figure from Takeuchi 1984, there are three types of motion for blowing snow particles, with increasing wind speed the main variable responsible for lofting snow particles. Drifting snow would equate to the rolling and saltation motions, while blowing snow would equate to the suspension motion. The ability for snow particles to become suspended and associated lowering visibility is also affected by air temperature and the characteristic of the snow. As you can see from the blowing snow thresholds figure, calculated by Dave Begley from Environment Canada, temperature and snow age also influence the likelihood of blowing snow. For example, given a constant wind speed and snow age, the likelihood of blowing snow will decrease with increasing temperature, or in other words, it requires a greater wind speed near 0 degrees Celsius to produce a lower visibility from blowing snow than it would at minus 15 degrees Celsius. One of the two methodologies merged into the Forecast Builder blowing snow tool utilizes the ARX study, which is based on blowing and drifting snow observations at a couple ASOS sites in southeast Minnesota and southwest Wisconsin, with wind speed as the primary input. This method highlights the lower end impacts and takes into account drifting snow. However, this method does struggle with the influence of snow age and temperature and tends to overestimate impacts, especially at warmer temperatures. As a side note, this tool will start to produce drifting snow or patchy blowing snow at 17 knots. You may be asking yourself why 17 knots or 20 miles per hour. The figure displayed in this slide is from Matsuzawa, which is taken from Takeuchi et al. In 1986, and shows that the impacts due to drifting snow start to increase quickly around 17 knots. You may also be asking yourself, what will be the frequency of forecasting drifting snow or patchy blowing snow if we use 17 knots as a threshold? A local study from the Aberdeen office showed that a 17 or greater knot wind threshold during the winter months occurs about 15 to 20% of the time in the northern plains, which seems reasonable. The second methodology merged into the Forecast Builder blowing snow tool utilizes the Bagley blowing snow model, which is a statistical model based on a robust set of observations from the Canadian prairie provinces. This methodology uses snow rate, temperature, wind speed, and snow age as inputs, and outputs probabilities of reaching certain visibility thresholds, including 3 miles, 1 mile, and a half mile. Because this method utilizes a robust set of observations and takes into account all the main factors that influence blowing snow, it tends to do a better job highlighting the characteristics of true blowing snow. For example, blowing snow that produces impactful, lower visibility to the public. For example, at temperatures near freezing, this model requires significantly stronger wind speeds to produce blowing snow. However, because this model was calibrated for true blowing snow, it will not account for drifting snow. In a recent Central Region Tech attachment, it was shown that the output of this blowing snow model correlates favorably with the impacts due to blowing snow. The Forecast Builder tool combines the best of the two existing blowing snow processes. It leverages the hourly wind speed, temperature, snow age, snowfall rate, and a majority of the precipitation not falling in liquid form. It also provides checks to account for drifting snow situations and is completely contained within Forecast Builder. Thus, there is no need to run a separate procedure, adjust values in a GUI, and all the offices use the same calculation. With the focus on impacts, the blowing snow values are assigned to match the impacts experienced from increasing probabilities of lower visibilities due to blowing snow. You can see those probabilities on the slide. As forecasters, we have a good understanding on the traditional elements going into the blowing snow calculation. But what is snow age and how is it calculated? As you would expect, snow age represents how old the snow is in hours. The values are calculated by a combination of snow observations and forecasted snowfall. From calibration studies of the tool, there was limited impact in the output as snow age increased above 25 hours. Therefore, the tool calculates the current hour's snow age by looking at the GFE OBS database snow amount grid and resets the snow age to 0 hours for each time it encounters snow. For example, hourly snowfall amount greater than or equal to 1/10 of an inch. For future hours, the tool begins with the current hour's snow age and then resets the snow age to 0 based on the POP and snow amount grid. We want to be confident that enough snow will be falling in order to reset the snow age to 0 for future periods, and thus the reason for looking at the POP grid in addition to the snow amount grid. The blowing snow output also factors in the amount of blowable snow that is present on the ground. To do this, the no-risk snow depth is used as a starting point. Internally, Forecast Builder will look back at the past 7 days of temperatures to see if they were warm enough to crust over the snow. The threshold for crusting over the snow is an hourly temperature of 35 degrees or warmer. If that temperature occurs, it will set the snow depth to 0, implying that the snow isn't blowable anymore. In addition to the check for the past 7 days, the same check will be applied into the future based on your hourly forecasted temperatures and snowfall. But before the calculations are made into the future, Forecast Builder will prompt the forecaster to verify the current snow conditions. This gives the forecaster the ability to apply their local knowledge on the current snowpack conditions and make adjustments to the areas that are blowable or unblowable. Keep in mind the amount of snow is not important, just focus on the thresholds seen on the slide. When the snow depth is 0, no blowing snow is allowed. When the snow depth is 1 inch, only patchy blowing snow is allowed. And when the snow depth is 2 inches or greater, the full blowing snow calculations are used. When approved by the forecaster, this final observation grid will be the one used when moving forward in the forecast. To better explain the snow depth calculations, let's take a look at an example from North Dakota in early March 2018. Looking at North Dakota, which is highlighted in the white outline, we can see that the entire state has at least 2 inches of snow on the ground based on the no-risk analysis. But later on in the day, temperatures are forecast to increase over the southwestern portion of North Dakota. At 18Z, temperatures are still expected to be below freezing, but they are forecasted to warm into the upper 30s by 0Z. Based off the temperatures during the afternoon hours, greater than or equal to 35 degrees, the snow depth grid is set to 0 during the hour that occurs and will stay that way until at least 1 inch of snow is forecasted. Here's a loop of the evolution of the blowable snowpack during the March 8th through 10th period in North Dakota. In the loop, you can see the values set to 0 in the southwestern North Dakota as temperatures rise above 35 degrees. Then, later on March 10th, you can see new snow accumulating from the forecast over southwestern and southern North Dakota, increasing values to 1 inch and making patchy blowing snow possible in that area again. The initial GUI with the blowing snow calculation is a quick question on whether you would like to have blizzard wording added to the forecast. It is recommended to only choose yes in the first 48 hours, or as confidence grows in the potential for blizzard conditions. By selecting yes, the weather grids will contain a quarter-mile wording with definite blowing snow for locations that have an 80% or greater probability of visibilities below a half mile. By using this discriminator, offices can leverage that weather key or the PoWT blowing snow grid to update DSS graphics for our partners and public. Like the weather grid, the PoWT blowing snow grid has become a derived element. This leads to the output being highly dependent on the input from the base grids: wind, snow age and rate, temperature. If you find that blowing snow output is not matching your expectations, first check the base grids, especially temperatures and wind speeds. Increasing your wind speeds will lead to increasing blowing snow output. As with all elements within Forecast Builder, make sure to collaborate any changes to the base grids. To end this presentation on the blowing snow methodology in Forecast Builder, we thought we would address the common questions that forecasters have asked during testing. In the first scenario, you run Forecast Builder for blowing snow and notice that the blowing snow is much lower than what you would expect with sustained winds at 25 knots. In cases with high winds but low blowing snow values, is usually tied to temperatures that are nearing freezing. In both the Begley and the Matsuzawa studies, they found that blowing snow rapidly diminished as temperatures rose above -2 degrees Celsius or 28 degrees Fahrenheit. In the second case, when driving to work this afternoon, you notice that there are small streamers of snow going across the road. You check both the OBS and the forecast and they have winds of 14 knots. But we don't have blowing snow in the forecast. Why not? In this case, you have to ask yourself if the blowing snow is impactful. Most of the times, these cases are not impactful. But that can change if there is plenty of sunshine causing road surface temperatures to rise above freezing, leading to melting and then refreezing of the blowing snow or drifting snow on the roads. At this time, Forecast Builder is unable to model the evolution of road weather conditions. This completes the Blowing Snow and Forecast Builder training module. Thank you for your attention.